we're going to actually draw this vector out and then talk about what we're looking for in terms of the unit vector in the same direction as this. So I'm going to give myself a coordinate plane here. You guys can do the same, like this and like this. Okay, so this vector is going to be 5 to the right. So it's 1, 2, 3, 4, 5. So that's my horizontal component. 12 down, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. That's pretty good. So this vector actually looks like this. Would you guys agree with that? This vector looks like this, and we'll call this vector v. Is that true? You guys cool with that? That's a pretty, yeah, cool, right? That's a long vector. In fact, what is the length or the magnitude of that vector? So remember how to do this? So the magnitude of this vector is equal to the square root of its component squared. So 5 squared plus, we've got this negative 12 squared. So this is looking like the square root of 25 plus 144. So this is looking like 169. Oh yeah, awesome, 13. Right? So this has this magnitude is 13. The vector has a magnitude of 13. Okay, fair enough. Now, if we want to find a unit vector in the same direction as the vector that's given, that whole length is 13, right? We want to find a unit vector in terms of I and j. So a unit vector needs to be how long if it's the unit vector? How long is a unit vector, you guys? 1, a length of 1. So could you draw on top of this vector what we're actually looking for? We're looking for a unit vector. That means it has to have a length of 1 in the same direction. So are we looking for a big vector or a small vector? Small. We're looking for a small vector. Very good. So it would look like this. The thing that we're actually trying to find is a unit vector in the same direction as the one given. So this one right there, this is a unit vector in the same direction. Okay, so to find the length of this unit vector, and remember this is like 13 of these little vectors like added up in a row here, right? We just want to how to describe one of them. And yes, we can put them anywhere in the plane because as long as they have the same direction, that's what we're looking for. So we're basically taking our magnitude, right? And we are our length and our vector, and we're dividing it by our magnitude. So our original vector is equal to this, 5i minus 12j. That's our original vector. We're going to divide that by its magnitude to give us a unit vector that's in the same direction. So we're going to divide that by the magnitude, which in this case is 13. So this is going to be the way that we do this. We're going to take our vector and divide it by its magnitude. So therefore, here's what we get. We get 5/13 I minus 12/13 j, and this is our unit vector in the same direction as the vector that's been given to us. So if you think about it, that means that we're going over 5/13 and we're going down 12/13 of a vector itself. So now then, how do we check to make sure that we did this right? Well, if we're going to check, that means that the magnitude of the unit vector needs to be what? What's the magnitude of the unit vector have to be? 1, yes, very good. So let's check and see. What's the magnitude of our unit vector here? Well, it would be the square root of 5/13 squared plus a negative 12/13 all squared. That's going to give us the square root of 25 1/69 plus 144 1/69. Oh, look at that. Check it out. That's giving me the square root of 169 over 169. Awesome. That means we have 1. All right, 4i minus 3j. Again, we're going to try and find the unit vector in the direction of 4i minus 3j. So we're going to start by drawing a graph. All right, and this vector goes 4 over 1, 2, 3, 4, 1, 2, 3. So we're looking like here is the vector that I'm trying to describe. I'm going to call this vector v. All right, what's the magnitude for vector v, everybody? If this is 4 and this is 3, what's our magnitude have to be? 5. Yes, very good. We have a magnitude of 5. So what I'm looking for, what I want to just be able to describe, and I'll choose blue, is I want to describe, if I was going to break this magnitude up into fives, because it's 5 units long, so into fifths. So I'm looking for something like that. That's what I'm trying to describe. So our unit vector is going to be our original vector divided by our magnitude of that vector. So it's looking like 4i minus 3j, all divided by our magnitude, which we just found to be 5. So it's looking at 4/5 I minus 3/5 j. And that is our unit vector in the direction of the vector given. All right, we haven't been able to actually really talk about vectors in their true sense because we haven't brought the concept of direction into the picture yet. So we want to be able to describe vectors in terms of their direction and their magnitude, and we've spent a lot of time on magnitude. That's not the issue. The issue then is how do we bring in the angle part to it, okay? So you only have 2 pieces of information right now. You know that a vector has a length of 6, or magnitude, and some 30-degree angle. All right, so here's what we're going to do. We're going to actually put up a coordinate plane and see if we can make some connections here. So if I call this x and I call this y, and I put the initial point of that vector at the point of origin, since we can put it anywhere in the plane, and I'll use pink to describe it, and I draw a vector, my magnitude is equal to 6. Is that true? And the angle that it's making in this coordinate plane, we've been given an angle of 30 degrees. A theta is equal to 30 degrees. Okay, let's break down its component parts. So how would I label this part right here, just in generalities? How would I label this part of it? What would that be? Is that the AI or the BJ part? This is the AI part, okay? What about, and well, in this particular case, yes. Yeah, we're making that. What would this one be over here, this vertical part? How do we describe vertical components? The BJ part. Okay, very good. Now, we know something about trigonometry. We definitely know something how to relate what we have on the page. So I'm going to ask you to do 2 things then. I'm going to ask you to tell me what is the sine of theta in terms of what you see on the page. The definition for the sine of theta would be what? Very good. It would be the BJ component part all divided by 6. Now remember, we represent vectors in terms of the BJ part and the AI part, the component parts. So could you solve that little tiny equation over there for the BJ part? What would it be? It would be 6 times the sine of theta. Is that true? That's all it would be, right? 6 times sine theta? Okay. And then what does the 6 part represent in the picture? The hypotenuse, but the hypotenuse, the magnitude, right? So what happens then, check this out. If I just work backwards in generalities here, the 6 represent the magnitude. So it's the magnitude of our vector multiplied by the sine of any angle given to us. So now we have a new way to describe the BJ component. It's magnitude times sine theta. And because of this little tiny picture right here. So I wonder now then if you could come up with the way to describe the AI part. What do you think it's going to be? It's going to be cosine, right? And here it is. The cosine of theta is equal to the AI part, all divided by 6. That's the definition. So therefore, the AI part has to be 6 times the cosine of theta. So that means that our AI part is equal to the magnitude of our vector times cosine of theta. Oh, check that out. Now we have a new way of describing the AI part. So if you put these 2 pieces of information together, in general, and this is the sort of the culminating part here, in general, we can represent any vector by its magnitude multiplied by cosine theta, and this is going to give us our I component, plus its magnitude times sine theta, and that's going to give us our j component. So in general, this is what we have. This is the important part here to describe it. And I didn't want to just tell it to you. I kind of wanted to explain it to you where it comes from in terms of an example. So now that we have that, we're going to go back and actually write that vector, the example one, in terms of our new way of describing how a vector works. So that being the case, here's what we get. Our vector, this vector up here, is going to be the magnitude, which is 6, times the cosine of 30 degrees, and that's going to be our I component, plus 6 times the sine of 30 degrees, and that's going to be our j component. So we can now represent this vector as 6 times, okay, everybody knows this one. What's cosine 30? Rad 3 over 2. There's my pre-calculus class. Awesome. Rad 3 over 2i. Good. Plus 6 times, what's the sine of 30? 1/2 I. So ladies and gentlemen, we get this. 3 rad 3i plus 3i. And now we have the official way of really representing a vector in terms of both magnitude and direction. Yep, this is a j. Thanks. J, j. There we go. So let's do this one together, right, where the numbers aren't so nice. Okay, we have a vector with a magnitude length of 1/2 at an angle of 113 degrees. So if we were going to draw this, what would it look like? Well, where's 113 degrees? What quadrant is that in? The second quadrant, right? Very good. So it's a little bit past this, so something like that, right? So there is my theta of 113 degrees. And what do I know about the length of this vector? The length of this vector is 1/2. Okay, good. So here we go. We can describe vector v is equal to the magnitude, which is 1/2, times the cosine of 113 degrees. That's going to be our I component, plus 1/2 times the sine of 113 degrees, and that's going to be our j component. So we need calculators out. One of these is going to be negative, right? Is the cosine going to be negative or the sine going to be negative? The cosine will be negative because it's in quadrant 2. All right? So make sure your calculator is in degree mode. And you guys can go ahead and work ahead of me. All right, we'll bring this into play for you. We'll shut this down. So mine's never in degrees, so I got to go to degrees, push enter. Okay, so if I do 0.5 cosine 113, what are you guys getting for that part? I'm getting like negative 0.2. Is that cool with you guys? Yeah. Okay, so this is going to be like negative 0.20i, and then plus, figure out what this one is. Yeah, 0.5 sine of 113. I'm getting like 0.46 j. Okay, cool. So plus 0.46 j, and this is how we represent this vector here. All right, let's work backwards now. Let's say that instead of me giving you a magnitude and an angle, and you coming up with the component parts, let's work in reverse. I've given you a vector broken down by its components. What is its magnitude and what is its angle? Well, let's draw it. Yeah, why not? That's a great idea. More visuals around here, right? So if I was going to draw this, I'd go over 2, 1, 2, and down 8. 1, 2, 3, 4, 5, 6, 7, and 8. So my vector would be looking like this. Here is vector v. That's equal to 2i minus 8j. So what's the magnitude of vector v? Square root of 2 squared plus negative 8 squared. That's the square root of 68? Good. Not necessarily all that nice of a number, but whatever, we can deal with it. Square root of 68. Okay, great. So the angle that I'm looking for is this angle here. This is my angle theta, if I'm in the coordinate plane. I have a right triangle here. So I wonder, could I get maybe this angle right here, this little one? If I call this beta for now, that little angle in there. Could I get that? What do I know about beta? Well, think about it. There's a triangle here, right? If this little angle is here, this is 2, this is negative 8, what do I know? Tell me something that we know. Call this beta. Ah, there it is. Good. The tangent of beta is what over what?
Negative 8 over 2.
Very good. Negative 8 divided by 2. Therefore, beta is going to be the inverse tangent of negative 8 divided by 2. We need to get this, we need to figure this out. So on the calculators, what's the inverse tangent of negative 8 over 2? We'll do it together.
Negative 75.9.
Inverse tangent of negative 8 divided by 2. And look what we get. And we're getting like negative 75.9. Can I round that to negative 76? You guys cool with that? So negative 76 degrees. So what does that mean? That means that this angle down here is swung down at negative 76 degrees. So then the question then is, well, what's this leftover part that we're trying to describe? 360. Take away the 76. Right? What would that be?
284.
There you go. So the angle would be 284 degrees. So our angle would be 360 minus beta. So if I give you, or we're given a vector that has been broken down to its components, we can then find its magnitude, and we can find the direction that it's going in given an angle.